Yeah, good evening, everyone. Uh, Welcome to week number 7 of Discrete Mathematics. Okay, so today we'll be talking about graph theory, which is the main subject of week number 7. I'll be doing less of the introduction part, and mostly I'll be going into the 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 problems that we need to solve. Okay. And graph theory is a very rich area in mathematics and computer science. As you know, there are so many applications of graph theory, and in computer science, it is especially useful as a data structure. Right? You think of graphs as relations between certain data objects. Graph theory is incredibly useful. So now, what are graphs? Let us just begin quickly. A graph is just a tuple, okay, denoted by VE. Okay, this is one way to denote graphs, where V is a set of vertices and E is a set of edges. What do I mean by that? Let's say these are the set of vertices, okay, A, B, C, D, and these are the set of edges. And the edge set is a relation, as you can see. It is a relation on V cross V, right? So for example, if I want to make this particular, if I want to pictorially represent this graph, then what I'll do is I'll draw the edges. As we've seen before also, to show a relation pictorially, we can do it using graphs. So A to B, I draw an arrow. B to D, I draw an arrow. C to D, I draw an arrow. And D to A, I draw an arrow. Right. So this is my graph, and this is a special kind of graph which is called directed graph, because the arrows, which are called edges, have directions to them. Okay, but if I do not draw the directions, okay, let's say I do not draw the directions, this is what is called an undirected graph. Okay, and take note that undirected graph is as good as directed graphs, where if there is an edge from A to B, there is necessarily an edge from B to A. Okay, that means if A is connected to B, so A is connected to B, then B is also connected to A. So undirected graphs represent that notion, or in other words, the relation represented is symmetric, which means the edge set will not only contain AB, BD, CD, and DA, but it will also contain BA, BB, BC, and AD. Right. So this is what undirected graphs represent, and unless mentioned, okay, all the graphs I'm going to talk about in the problems, okay, will be undirected graphs, okay, unless mentioned otherwise. Now, quickly, what is the degree of a vertex? Okay, degree is just the number of edges incident on a vertex, which means that how many edges are incident on A. Okay, here is one edge, here is another, here is another. How many such edges are there? 3 edges. So the degree of A is 3. For B, what is the degree? B is connected to A by a one edge, and B is connected to C by one edge. So degree of B is 2. Total number of such edges. So similarly, what is the degree of C? 2. And the degree of D is, there's only one edge incident on D, so it's 1. Okay. Now, so that's about degree. Now, the final thing we need is the types of graphs. Okay. First type of graphs, which are pretty interesting and well studied, are complete graphs. So, complete graphs are graphs where there is an edge between each pair of vertex. if there are two vertices in the graph, they need to be connected by an edge. Okay. For example, the first one you see here. Okay. For example, the first one you see here, okay, is a complete graph on three vertices, because there are three vertices and all the three vertices are connected to each other. This is a complete graph on four vertices. There should be an edge. And this is a complete graph on 5. Oh, wait. Okay, yeah. Now it is a complete graph on 5 vertices. So these have names actually. In the graph theory community, this is called C3, C4, C5, and C6. Okay, sorry. Not these. That is for cycles. This is called K. Okay, K3, K4, K5, K6. Okay. This is a graph, complete graph on 6 vertices. So next we'll look at cycle graphs. Cycle graphs are just graphs, okay, that have what is called a cycle. What is a cycle? A cycle is a path, okay, which goes through vertices. Okay, it can, as a path can go through several vertices, but you are not supposed to repeat the vertices, and you finally end up, coming to the vertex where you started with. Okay, such a vertex, such a path is called a cycle. Now, this is a cycle on 3 vertices. This is a cycle on 4 vertices and 5 vertices, and so on. So cycles are represented by C4, C5, C6, and so on. But now, please note that cyclic graphs are something slightly, cyclic graphs is a slight more generalization. In cycle graphs, the graph itself is a cycle. However, in cyclic graphs, they are graphs which contain a cycle. Or in the lectures you've seen the concept of subgraphs. They have a cycle as a subgraph there. Okay. For example, this particular graph. Or for example, can you tell me if this is true? All complete graphs are cyclic. Okay, and the same statement, right? All complete graphs are cycles. Which one of them is true? Or are both of them true, or are both of them false? Okay. This is statement 1, this is statement 2. One is true. Yeah, that's right, Akansha. Statement 1 is true. Why? Because what is a cyclic graph? It is any graph that contains a cycle. Okay. For example, see K3, it contains a cycle. K4, does it contain a cycle? This is a cycle, right? And K5, does it contain a cycle? Yeah, this is a cycle. K6, does it contain a cycle? Yeah, you can trivially consider this as a cycle. So each of the graphs, okay, each of the complete graphs, this is not a formal proof, remember, but I won't go over the formal proof. But of course, I mean, via examples, you can kind of see why complete graphs actually are cyclic, because they contain a cycle. But now what we are saying, all complete graphs are cycles, which means the graph itself is cycle. We are not saying that a part of the graph is a cycle. So that happens to be not true. Why? If we look at K3, okay, it is a cycle. Good, the statement holds in this case. But K4 itself is not a cycle. K5 itself is not a cycle. It is much more complicated. See, this is not equal to this, right? So therefore, these are clear counter examples to the statement. So this is false. Okay, the second condition is false. The second statement is false, and the first one is true. Okay, good. Now let us look at the other end of the spectrum. What are graphs that do not contain cycles? They are what are called trees. Okay, they are graphs without cycle. Actually, I'm abusing one definition here, that they should be connected graphs. They are connected graphs without cycle. Okay, for example, this is a tree, this is a tree, and this is a tree. Okay, they do not have any cycles. Now what I mean by connected here is very important. I think it is done in the lectures, but I'll just mention once. Okay, I'll give an example. This is a graph which is not connected. Okay, this is a graph which is connected. Okay, because you can see that there are clearly two vertices that are not reachable from each other, right? So they cannot reach each other, and therefore the component that they lie in are called connected components. How many connected components are here? Only one. How many connected components are here? Two connected components. And a connected graph means only one connected component. Okay, and this is vice versa. If there is only one connected component, then the graph is connected. Okay, so a tree necessarily needs to be connected. Okay, it is not enough to say that okay, the graph does not contain cycles and the graph is disconnected. It needs to be connected, okay, to be a tree. Yeah, next thing is regular graphs. The final thing we'll look at is regular graphs. These are graphs where the degree, okay, is same for all the vertices. For example, now to recap, what is the degree? Degree is the number of edges that are incident on a vertex. For this vertex, there is only one edge, so the degree is 1, and the degree is 1 here. For this vertex, what is the degree? There are 2 edges incident, so this is 2. For this also there are 2 edges. For this also there are 2 edges incident. Next, again you see that each of the vertices have 2 edges incident on it, so the degree is same for all. Here let us check. Can you tell me if this graph is regular or not? In other words, can you check whether the graph has same degree for each vertex or not? Akansha is not regular. Okay, can you tell me which vertex? Why is it not regular, Akansha?
Sir, it's regular. All degrees are 3. Earlier the figure was small, so I didn't see.
Okay. Okay, I'll make sure I zoom into figures. Yeah, that's right. So, right, this is a regular graph because each vertex has 3 edges instead. For this vertex there are 3 edges. For this there are 3. For this there are 3. There are 3, and so on. Right. So all of them are 3, 3. This is not vertex, yeah. And so on. So this is still a regular graph. Or more specifically, this is what is called a 3 regular graph. right? This is what is called a two regular graph. So you can immediately see that there is no unique D regular graph. Okay, for a certain degree D, there can be several D regular graphs. Because this is a two regular graph, this is also a two regular graph. Both of these are two regular graphs. Okay, good. So let us start solving questions. The first question is as follows. Consider the following graph. Okay, which of the statements is true about G? G is cyclic, not regular, but complete. G is regular, cyclic, but not complete. G is regular, not cyclic and complete. Neither regular nor complete but cyclic. So I'll zoom it a bit. Okay. So can you think about it for a while? Which of these options are correct? Okay, our answer is B. So G is regular, cyclic, but not complete. Okay. Yeah, good. That is correct. Now let's see why. Because okay, let's check for each of the properties. Okay, let's check completeness, whether it's a complete graph or not. What is the property for complete graphs? Every pair of vertices should be connected with each other. But when we stare at it, edge CD is not there. Right. There's no edge like this. But if it were to be complete, then it should have had this edge. So, or you can give any other example like BA or something. So this is clearly not complete. So we are down with this option is definitely there and not there, and this option is definitely not there. So we are left with checking regular and cyclic, right? So is it regular? Now check the degree of each vertex. Degree of A. What is degree of A? A is connected to two vertices. So 2. Now check degree of B. Degree of B is also 2. And keep checking. Degree of C is also 2. Degree of D is also 2. Degree of E is also 2. So equals degree of C D E. Therefore it is regular or 2 regular. Right, so good, it is regular, and well, this option is also not correct, which means so B is the correct answer from here. But we can also check for cyclic anyway. So this graph, it is cyclic. Why? Because in fact it is a cycle. It is a stronger statement. It's not just cyclic, but it is a cycle, because I can rewrite it as this way: A D E, right, and D goes to, I'll flip B and C here. B, I'm just flipping them together. Imagine them to be some balls connected by threads. Okay, I'm just flipping the balls. B here, Remember that I'm not changing the relationship they have, the edge relationship that they have. C here, C is connected to A. These two are same. Okay, or in the graph theory world, these are what are called isomorphic graphs. So these two are same, and you can clearly see that this graph contains a cycle. Okay, therefore it is cyclical. So clearly the answer is B. Okay, because B says regular cyclic but not complete. Okay, good. Okay, so the next question says the following: G is a complete graph on 27 vertices. The number of edges in G are. So again, I'll give you a few moments to think about the question. Well, you can think about it combinatorially also. Okay, this is a very combinatorial. Much of graph theory is combinatorial, and this is a simple combinatorial argument. But there's also a formula to do this. So if you already know the formula, Akansha says P. Okay. Let's see. The formula is as follows. Okay. If there are n vertices, okay, for an n vertex graph, complete graph, number of edges is n times n minus 1 divided by 2. But this is nothing but n choose 2. Right. Why is it the case? Okay. Let's say I have 4 vertices. Okay. And I'm seeing, because this is complete, each vertex is connected to every other vertex. So this is as good as I'm choosing where to place my edge. Okay, I can place my edge here, I can place my edge here, I can place my edge here. I can place edge between these two, I can place edge between these two, and I can place edge between these two. And these are the empty spaces, right? And between them I can put an edge like this. And how many such spaces are there? Well, it is as good as choosing a pair of vertices, right? So number of places to put edge is nothing but choosing two vertices at once, choosing a pair of vertex and putting an edge between them, which is nothing but n choose 2. Okay, which is nothing but n choose 2. So which is n times n minus 1 divided by 2. Yet another way to think about it is this way. If I have 4 vertices, then each vertex, if it is complete, each vertex will be connected to 3 other vertices. This will be connected to 3 other vertices, and so on. This will be connected to 3, and this is how it goes. So if I have an n vertex complete graph, degree of each vertex is 3, which is like n minus 1 in our case. So each of the n vertices are connected to n minus 1 other vertices. Okay, but since we are overcounting, for this vertex we counted this edge, for this vertex also we counted this edge twice, so we are divided by 2. We can do this also. So therefore the answer is 27 vertices, right? So 27 times 27 minus 1 divided by 2, which is equal to should become 702, I guess, divided by 2, which is nothing but 351. So the answer is B. Okay. B. Yeah, that's right. D is the answer. Yeah, here is another interesting question. Okay, something to do. You can combinatorily do it again, or you can do it by example also. Given a tree T with 2048 vertices, what is the number of edges in the tree? So, okay, that was quick. Okay. Let's see. So, let's just see a tree with, two vertices. Number of vertices is 2. Number of edges is 1. This is another tree. Number of vertices is 3. Number of edges is 2. Here is another tree on 4 vertices, right? So number of vertices is 4, number of edges is 3. I can make another 4 vertex tree this way. Number of vertices is 4 and number of edges is 3. Oh, and so happens that experimentally, okay, while doing, I'm getting that the number of edges is 1 less than v minus 1. And this is not a coincidence, this happens to be true for all trees. And I think this was done in the lectures, so I'm not going to do the proof for it. But it is not very difficult to prove also. But it needs some kind of inductive reasoning that, as soon as the idea is that in a tree, okay, you inductively assume that there are m edges. As soon as you put another vertex to it, you connect it with an edge like this. So the number of vertex and number of edges also rise together. So again, you have the difference, the difference between number of edges and number of vertices is the same thing. But anyway, you don't need to know all that. The main idea is that the number of edges is the number of vertices minus 1 for every tree. So here number of vertices is 2048. This means the number of edges is number of vertices minus 1, which is 2047. Okay, and this is which one is this? This is yeah. Okay, so the answer is B. Yeah. So yeah, you were right, Akash. Okay. So let's look at this one. If a graph has 5 vertices but degrees 1, 1, 2, 3, 3, what is the number of edges of the graph G? If a graph has 5 vertices with degrees 1, 1, 2, 3, 3, what is the number of edges of the graph G? So okay, I'll solve this one. So this question, okay, depends on the handshaking lemma or the handshaking theorem. The handshaking theorem, okay, one of the first things in the lectures is that the summation of degrees or the sum of the degrees of the vertices, okay, is equal to twice the number of edges. This is what the handshaking lemma says. Okay, and so in our case, the degrees are 1, 1, 2, 3, 3. So we are going to do 1 plus 1 plus 2 plus 3 plus 3. Okay, which is nothing but 10 equals 2 times number of edges, which means that the number of edges is 10 divided by 2, which is equal to 5. So the answer is 5 and B is the answer. Okay, so this is a direct application of Einstein lemma. Please let me know if this is fine. Okay, or if you would want me to repeat this. I'm not doing a proof to the Einstein lemma because it's already done in the questions, the lectures, I believe. Okay. Yeah. Anyway, let's move on. Akanksha should be, yeah, that's right. Okay. Okay. Right. B5 is the answer. That's right. Good. So yeah, here's another nice one on the property of graphs. Okay. Divya, is it fine so far? Please let me know if you want me to repeat something, okay? Okay. The question is as follows. Alice tells Bob that she has a connected graph with 32 vertices and 25 edges. Bob is not sure if Alice is telling the truth. Find out if Alice is lying. So can you try this? It relies on a certain fact, which I believe, yeah, which is done in the lectures. There's a simple fact to, connected graphs. So Alice says that she has a connected graph with 32 vertices and 25 edges. Oh, okay, okay, she's lying. Yeah, okay. Can you tell why she's lying? Okay. Yeah, well, it is true. I mean, it is true that she's lying. I mean, the key thing here, okay, the key point in this question is that the graph is connected. If this word was not mentioned, then we could not say anything whether Alice is lying or telling the truth. But the key thing here is connected. Okay. What is the fact? Connected graph G on on n vertices has at least n minus 1 edges. You can try it, make a connected graph. This is a connected graph. How many vertices are there? 1, 2, 3, 4. How many edges are there? 1, 2, 3, 4. This is a connected graph. 3 vertices, 2 edges. Here you have 4, 4. Here 1, 2, 3, 4, 5, 6, 7. 7 vertices. How many edges? 1, 2, 3, 4, 5, 6. 6. Nothing. No number of edges. No graph is exceeding, n minus 1 number of edges. So this is the fact here. Okay. And the argument is that if, Alice had a graph, okay, with 32 vertices, right? If she had a graph with 32 vertices, then number of edges needs to be at least 32 minus 1, which is 31. But she has how many? 25 edges, which is clearly less than 21. Which is clearly less than 31. So clearly Alice is lying. Okay. So please let me know if there is anything here you do not understand. The main fact is, okay, the theorem is that, a connected graph, okay, it's not a connected graph, it's a connected graph. If a graph is connected, then it should necessarily have at least n minus 1 edges if it has n vertices. But Alice has 32 vertices. The graph which Alice has 32 vertices, so she should have at least 31 many edges. That's the idea. Okay. Okay, good. Let's look at the next one. Yeah. So another combinatorial question. Given a graph G with k connected components, recall the connected components I discussed earlier. Given a graph G with k connected components, each having n1, n2, n3 and so on till nk vertices respectively, then the maximum number of edges G could have is so which one of the following would be the answer? Take a look at the questions and think about it. Okay. Consider A. Wait for a while. Yeah. Okay. Yeah. Let's see the answer. So what are the information that we have here? So firstly, there are k connected components, and we know the number of vertices in each of these components. Okay. So let's say the graph looks like this, and this is, you know, the C1, C2, C3, CK. These are the connected components, and they do not have edges between each other. This is what connected components means. But they may have edges with each other. So what are the number of vertices we know about them? We know that this one has n1 number of vertices. This one has n2 number of vertices, n3 and nk number of vertices. Okay. So the maximum number of edges G could have that is what they are asking. Well, the first thing you would try in such a question is just give all the edges to all the vertices, across all vertices. But what if I give an edge like this, a vertex here to a vertex here? Now that is not allowed, right? Because if you do that, if you give edges like that, then these two would make one single connected component. So the idea is that you are not to distribute the edges between two connected components, but something like this is allowed. Something like this is allowed. Okay, if there are two edges, I can give two vertices, I can give an edge between them. So I want to find the maximum size of the graph G. The idea is that I'll find the maximum size of a single connected component, and how I do that is, if there are a pair of vertices, I'll just give an edge between them. And intuitively it does make sense that the number of edges is maximized if between every pair of vertices, okay, I put an edge. In other words, I make something like a complete graph. Okay, something like a complete graph. It's something like a complete subgraph. Okay, so I make the connected component as a complete graph. Here too I make a connected component as a complete graph. Why? Because maximum number of edges, okay, in a connected graph is achieved when the graph is complete. So what do I do? Make every connected component a complete graph or a complete subgraph. That is what I do. So yeah, make every connected component as a complete subgraph. Okay. So like the previous question, okay, recall that complete graph on n vertices has n choose 2, which is n times n minus 1 by 2 edges. Okay, call that complete graph on n vertices and n times n minus 1 edges, n minus 1 divided by 2 edges. Okay, so for a ni, okay, for number of vertices equals ni, I have ni choose too many edges, right? So in other words, here I have n1 choose 2 edges, another one I have n2 choose 2 edges, and I keep doing this for all n1 till nk. Therefore, total number of edges equals n1 choose 2 plus n2 choose 2 plus so on till nk choose 2. This is nothing but summation of ni choose 2. I equals 1 to k. Okay. So yeah, so if I compare, then this A is the answer. Yeah, good, Akanksha. Answer is A. Okay. Any questions until now? The key point is that the number of edges, okay, the number of edges in a complete graph is n choose 2. So consider each of the components as complete graphs. Okay. Now, yeah, let's move on. So the question is as follows. Which of the following degree sequences cannot be the degree sequence of any valid graph? So I'll give a hint. Okay. Use the Havel Hakimi theorem. So this theorem was done in the lectures. So can you try once? So these are what are called degree sequences. These are degrees of vertices in decreasing order. So the advantage of doing this is, you can check whether a graph is valid or not, whether such a graph even exists with the following degree, with a particular degree sequence. Okay. Well, the Havel Hakimi theorem, okay, gives us a nice algorithm actually to check whether a degree sequence is valid or not. How do we do that? Well, let's say I have a degree not 5. Let's say I have a degree sequence as 3, 3, 2, 2, 1. Okay. Then what I do is I actually, if there is a 3 here, I'll pick the next 3 here and I'll keep subtracting 1 from it. Remove this, and then to this do 3 minus 1, to this do 2 minus 1, and to this do 2 minus 1, and leave this 1 as is, because since this was 3, I just want to work with the next 3 elements, that is these 3 elements. Okay, so which is nothing but 2 1 1 1. Next thing what I do is since there's a 2 here, I choose the next 2 elements and subtract 1 each. So this will not be there, and this will become 1 minus 1, 1 minus 1, 1, which will become 0, 0, 1. Now this is not valid. What we need is something like 0, 0, 0, or 0, 0, 0, 0, or a string of zeros, That is what we need. And this is an example of an invalid sequence. Okay. But if it was, just 3, 3, 2, 2, then, this will become 2, 1, 1, and this will become 0, 0, 0, 0, 0, then this is valid. Okay. Maybe we can even try constructing it. There are 4 vertices. This is 3, and this is 2, and this is 2. This is an example of a graph which is follows the degree sequence. So this is valid. So that is exactly what we'll do. Now let's do it one by one. So E says 7 6 5 4 4 3 2 1. Let's try. This becomes, remove the 7, choose the next 7 elements. 5, or to the first one at least I'll write 6 minus 1, 5 minus 1, 4 minus 1, 4 minus 1, 3 minus 1, 2 minus 1, 1 minus 1. So this will become 5, 4, 3, 3, 2, 1, 0. Now let's do once again. Remove this 5, do 4 minus 1, which is 3, 3 minus 1, which is 2, 2, 1, 0, 0. Now the next 3, 1, 1, 0, 0, 0. Next one, remove this 1. This will be minus 1, 0, 0, 0, which is 0, 0, 0, 0. So happens that the first one we tried itself was a valid instance. So the answer is A. But let's try, whether the others are invalid or not. For example, B, let us try. 4 6s, 2 3s, and 2 2s. Okay. So this is what we have. Okay. Now remove for the next 6 elements. Okay. Do 6 minus 1, 3 minus 1, 3 minus 1, 2 minus 1, 2. So this will become 5, 5, 5, 2, 2, 1, 2. Now since there is a 5, you have to take the first 5 elements. Okay. Now this will become 4, 4, 1, 1, 0, 2. Next, 4 here, so take the first 4 elements, and this will become 3, 0, 0, minus 1, 2. As soon as you see a minus 1, this is a red flag. You cannot, eventually when you reach this, you cannot do, minus 1 something, minus a positive number, and then you get you get zeros. So you can stop at this process also. Or you can, continue subtracting, but this will not lead you to 0, 0, 0. So this is invalid. Okay. I'll just do one final one, and D you can try it yourself. 7 6 6 4 4 3 2 2. 7 6 6 4 4 4 3 2 2. Okay. 7 6 6 4 4 3 2 2. Let's try that. Take the first 7 and do -1. Now there's 5, so take the first 5 and subtract 1. So 4 2 2 1 0 1. Take the next 4 and subtract 1, then you get 1 1 0 minus 1 1. And this will clearly not work, you got a negative number. But you can continue, of course, choose the first one and then subtract. This becomes 0 0 minus 1 1. And then you cannot move ahead. So this is invalid. So the answer is, so D, you can try it yourself. Okay, the answer is A. A is a valid degree sequence. Okay, and you can try, since this is a valid sequence, you can try constructing an actual graph which looks like this. Okay, good. So I hope that was clear. I hope that is clear. So please let me know if you want me to repeat anything. Okay, Akanksha, Divya. Okay. Okay. Good. Yeah. So. Okay. I just have 3 more questions left. So this session, I don't know why it's going pretty early today. Anyway, okay, so we have 3 more questions. So the question is as follows: consider the following graph G. What is the number of spanning subgraphs of G? Okay, another nice combinatorial question. So just to recall, okay, I'll let you guys think about it, but just to recall, what is a spanning subgraph? Okay, a spanning subgraph, okay, is a subgraph with all elements, not elements, vertices, with all vertices of original graph. Example: if this is a graph, this is a subgraph, but not spanning. Why? All vertices are not present. For example, if this is labeled A, B, C, D, and this is A, C, D, then B is not here. But this is spanning. Okay, all the vertices are there. A, B, C, D, everything is there. In fact, this is also spanning. Okay, as long as all vertices are there, this is a spanning. This is not connected, but we never said we needed a connected subgraph, right? A subgraph could be not connected. So now please try the question. Question says the number of spanning subgraphs are. Okay, sorry. Yeah. So this is the graph, and how do you count the number of spanning subgraphs? And to give you another hint, the main this is the main thing here. Okay. Okay. Let us try to solve this. This is our original graph. So again, I tell you, spanning subgraph is a subgraph where all the vertices need to be present. So all these vertices need to be necessarily present. B, C, A, and what is there? D, E. Oh, it seems there's a slight mistake in the question. Or is there? How many edges are there? Okay. Let me remove one edge. Let's say this edge was not there. Okay, let's say this edge was not there. Now we need to remove from here also. Yeah. So this was the graph given. So what is a subgraph? What is a spanning subgraph for this graph? Okay. Well, I can remove this edge and say, okay, this is a spanning subgraph because all the vertices are present. I can remove this edge and say that, okay, all the subgraphs are present, all the vertices are present, and the edges are also present in the original graph. So this is a subgraph also, this is a spanning subgraph also. And well, I can say, okay, let me keep this, but remove this edge. Or let's say I remove this and introduce this edge. Or let's say I remove all edges. This is still a spanning subgraph. Point is, I have two choices. Point is, I have two choices. Either put the edge or not. If I place the edge, also it will be a spanning subgraph. If I remove the edge, also it will be a spanning subgraph. Right? So there are two choices for, let's say, DE, two choices for AE, edge AE, and so on. Two choices for each. So this means that by the product rule, total number, and each of these choices causes a new spanning subgraph to be formed. So the total number of spanning subgraphs equals 2 to the power, okay, 2 times 2 times so on, right? And how many of these 2's are there? How many ever number of edges are there? Which is equal to 2 to the power number of edges. And what is the number of edges here? 1, 2, 3, 4, 5. 2 to the 5, which is equal to 32. And which option number is 32? 32 is C. Answer is C. So I hope this is clear to all of you. So yeah, I'll show this part. The point is, see, all of the vertices need to be present anyway. If the question was for any general subgraph, okay, then the calculation could be slightly more complicated. But since it is a spanning subgraph, I don't need to account for the choice of vertices out there. So all the vertices are necessarily present. I just need to choose the edges. Either choose whether B or B comma A is there. I mean, an edge between B and A is there. And then choose whether the edge B to D is there or not. I have two choices each, and each of these choices, true or false, will create a new spanning subgraph. Removing BA would create a new spanning subgraph. Keeping BA edge would make a new spanning subgraph, right? So I just multiply using the product rule to find the number of such spanning subgraphs. Okay, and how many choices are there? The number of choices is equal to the number of edges here in this case, and 2 to the power 5, which is 32, and the answer is finally C. Okay, I hope it is clear. But let me know. Okay, please stop me if there's anything that is left unaccounted for. So yeah, let's look at this question. Cut vertices. Okay, this is another nice thing about graphs. Question is, what is the number of cut vertices in G? I think this was done towards the end in the video lectures. But if you want to recap on cut vertices, also let me know. Okay, Akansha is D. What is D? D is 5. Okay. Okay. Let's see. So Akanksha, can you name those vertices?
Sir, H,
Okay.
G,
Okay.
E,
Okay.
B, C,
Okay.
and F. No, not F. Till C.
H, G, E, B, C, F.
Not F. H.
Oh, not F. Sorry.
Yeah.
Yeah. Okay. Uh, okay. Let's see if that is correct or not. Well, so I'll just quickly mention what a cut vertex is. Cut vertex is a vertex whose removal causes the graph to be disconnected. Okay. What is meant by disconnected? Okay. See. Cut vertex whose removal causes graph to become disconnected. What is meant by disconnected? Number of connected components is greater than 1. For example, if this is a graph, okay, and I remove this vertex, what is the number of connected components? Still 1. So that vertex was not a cut vertex. Not cut vertex. Okay. But if I remove this one, it will cause this to happen. And I clearly have two connected components. So this vertex is cut vertex. Now let us look at the question, okay? So I'll make a duplicate of this image. It's not happening. Oh, can I not? Okay, anyway, I'll just draw it then. H, G, E, B, C, F, D, E, A. So let me try. So if I always imagine like you are taking a pair of scissors and disconnecting it. So if I take a pair of scissors and disconnected this D, okay, how many components will be left? If I remove it, if I delete it, if I delete this D, how many components will be left? Just one component. So D was not a cut vertex. If I remove F, okay, how many components do I get? I get just one component. So F and D are clearly not cut vertices. But observe that if I remove, G, I get two connected components, one here, the other here. So if I remove E, that's it. Then I get two connected components here, one here, one here. If I remove, say, B, then how many connected components do I get? Two connected components, one here, one here. Okay, and if I remove C, then I get these two connected components. So you can see that these vertices actually disconnect. But if I remove A, for example, like this, then I just have one connected component. So yeah, and Akansha, you had said H also, right? All the others were fine, but if I delete H, if I remove H, this is what I get, and the graph is still connected. It is not getting disconnected. Okay, so the the cut vertices are G, E, B, C. So answer is 4. There are 4 connected components. Okay. I hope that is fine. So it's clear, right? Why Akanksha, why H should not be there as a cut vertex?
Yes, sir.
Okay. Okay, good. So yeah, this is the final question. It's a very simple question. The question asks how many connected components are formed when we delete all the cut vertices in the graph G. Okay, so can you try this one? And let me. How do I? Oh right, yeah, I have an idea. I'll take a screenshot of this. Okay, and then I'll just select this and copy. Copy it, right? Yeah, this is the graph. Yeah, so please try this. How many connected components are formed when we delete all the cut vertices in the graph G? So what are the cut vertices? Okay, in graph G are G, E, B, C. That is what we observed, right? Okay, Akanksha says C. Okay, let's see. If I remove G, then I get this component and this component. But we are not, asking the question in this way. We are asking what if we delete them all at once? Okay, then what will happen? So let's say we delete E also, and let's say we delete B also, and we delete C also. Since we delete them, the edges will also not be there, and this vertex is its own connected component. This vertex is another connected component. So is this, okay, and so is this. So number of connected components is 4 on deleting is 4, which means that the answer is C. What did you written? Yeah, that's right, Anand. C is the answer. So I hope this is fine. So please let me know, Akanksha, Divya, if this question, because we've entered the end of the sessions now. I mean, I didn't think that they would be completed so soon, but yeah. So this was fine, right? Or let me know if even if a previous question you want me to um, uh, solve again, or have some doubts there. Okay, no doubt. Okay, Divya, was it everything fine? Okay, no doubt. Okay, good then. We'll call it a day then. Okay, we'll meet next week again at 6 p.m. We'll do more on graph theory at a more deeper level. Okay then, good night to you. Okay, thank you. Okay, so yeah, thank you. Okay, thank you, Divya. Good night.